You know that feeling when you're typing and you know perfectly well how to spell the word the, but your fingers just keep typing TEH?
Oh, all the time.
It's not like you suddenly forgot how to spell. It's
Okay.
just a glitch, right? A hardware problem.
Exactly. It's the classic software versus hardware question. Did the plan in your brain fail, or did the machine, your fingers, fail to execute the plan?
And usually we can just hit backspace. But today we're doing a deep dive into what happens when you can't hit backspace. We're looking at speech disorders, specifically through a chapter by Gary Weismer.
It's from the book Psycholinguistic Perspectives on Developmental and Neurological Speech Disorders.
Yeah, a bit of a mouthful, that title.
It is.
But the question Weismer is asking is actually really simple. When someone makes a speech error, a kid, a stroke survivor, anyone, how do we know if it's a bug in the brain's plan or just a problem with the muscles?
And his whole point is that for a very long time, we've basically just been guessing. We hear a weird noise coming from a car and immediately assume the engine is blown.
When it could just be a loose part?
Right. He's really drilling down on the difference between just describing an error and actually explaining it.
So that's our mission for this deep dive. We're going to unpack that difference. We'll start with speech delay in kids, then get into this pretty wild idea called optimality theory, and then shift over to adults who've had strokes.
Sound good?
So let's start with the kids. The text talks a lot about speech delay. I feel like I hear people use that term just to mean a kid is a late talker. Is that right?
Not exactly. A late talker might just be quiet. A child with a speech delay, though, they're talking, but it's like they're sort of stuck in a time warp.
Oh, so?
Imagine a 6-year-old. They're bright, they understand everything you say, but when they talk, they sound just like a typical 3.5-year-old.
Ah, okay. So the mistakes they're making aren't weird or random.
No, and that is the absolute key. If a child is making really bizarre errors, things you never hear in normal development, we might call that deviant speech, or maybe something like apraxia. But a speech delay is just young sounding. The developmental path is normal. It's just.
Slow down.
Exactly.
So the hardware's fine, the software's just running an older version. This makes me think of the FIS phenomenon that's in the chapter.
Oh, the classic Burko and Brown study.
I love this one. It's so perfect for anyone who's ever had a circular argument with a toddler.
It really is. It just perfectly captures this disconnect between what a child knows and what their mouth can actually do.
So paint the picture for us. What happens?
Okay, so a child is looking at a fish tank and says, "Look at the fish." The researcher, playing along says, "Yes, that's a fish."
And the kid gets annoyed.
Totally frustrated. They get angry that you're agreeing with them but saying it wrong. The child says, "No, not fish, fish."
But they're saying the same word.
To our ears, yes. But then when the researcher finally says, "Oh, you mean a fish?" the child's whole face lights up. They say, "Yes, fish."
That's amazing. So in their head, the file is perfectly labeled FISH. They can hear the difference.
The input is perfect. The underlying form is correct. But the output, the production, is just blocked somehow.
So for a long time, the field called this functional misarticulation, which, it sounds very scientific.
It sounds scientific, but really it was what we call a wastebasket term.
Yeah.
It was a polite way of saying we have absolutely no idea what's causing this. It implies there's a problem with the machine, but we can't find the broken part.
But then things shifted. We started talking about phonological processes.
Right. The big idea here was that these errors aren't random misses. The kid is following a rule book. It's just a simpler rule book.
They're applying rules to simplify things.
Exactly, like a compression algorithm for speech. It makes hard words easier to say.
What's an example of one of these rules?
A really common one is final consonant deletion. The rule is simple. Just drop the consonant at the end of a word.
So dog becomes do.
And cat becomes cat.
Or I've heard of stopping, where a long hissy sound like S or F gets turned into a short punchy sound.
Yeah, a stop consonant. So sun becomes ton. And the breakthrough here was huge for therapy. Because if you know the child is using a rule, you stop just drilling the muscle over and over again. You stop making them practice the es sound 100 times. Instead, you treat the concept. You teach the rule.
You're debugging the code, not fixing the keyboard.
You got it.
Okay, that makes a lot of sense. But Weismer argues that we've now moved even beyond that into something called optimality theory. And I have to admit, this part of the reading got a little dense. Constraints, rankings. What is that all about?
Okay, let's simplify it. Think of it as that tug of war we mentioned. Every time you want to say a word, there are two big forces at play in your brain. The first one is called faithfulness.
Faithfulness to the original word.
Exactly. Faithfulness wants your output, what you say. to perfectly match the input, the word you've stored in your memory. If the word is stop, faithfulness is screaming, say stop.
Okay. And what's pulling on the other end of the rope?
Markedness. But an easier way to think of markedness is just laziness.
I can get behind that.
Markedness wants to make everything simple. It hates consonant clusters. It hates sounds at the end of words. It hates anything that's hard to pronounce.
And in a baby's brain, I'm guessing the laziness constraint is winning.
It's the five-star general. It outranks faithfulness completely. So simplicity always wins. Stop becomes top because it's just easier.
So getting older linguistically isn't about learning new things. It's about re-ranking those priorities.
It's about demoting the laziness general and promoting the faithfulness general. And this whole framework leads to this incredible paradox in speech therapy.
A paradox.
Yeah. Your intuition with a kid who's struggling is to start with the easy stuff.
Of course. Build their confidence. Pick a sound they can almost make.
That's what everyone thinks. But the research shows pretty clearly that's the slow way to do it. To get the fastest, biggest change, you have to do the exact opposite.
What? You target the hardest sounds, the ones they can't do at all.
You target the complex, non-stimulable sounds. The reason is you're attacking the hierarchy. If you can teach them to master a sound that's governed by a very powerful, high-ranking laziness constraint.
You break that constraint. You demote the general.
And when the general falls,
all the lower-ranking officers fall with him.
That's it. It's called an implicational relationship.
The text it had an example with. Was it rabbits in the color yellow?
That's the one. The Dinson and O'Connor study. They looked at kids with two common error patterns. The first is gliding, so they'd say wabbit instead of rabbit.
Okay, wabbit.
The second is consonant harmony, where different consonants in a word are made to match, so yellow becomes lello.
Wabbit and lillo. Got it.
So the theory says the constraint against saying their R sound is a really big boss.
Yeah.
A high-ranking constraint. If you treat the gliding, if you work really hard and teach that child to say R correctly.
You've taken down the boss.
And strangely, the harmony problem, the lello, often just disappears. It fixes itself for free without you ever working on it.
But if you go the other way, if you treat the lello first.
The wabbit problem almost always stays right where it is.
Yeah.
You've only dealt with a minor officer. The general is still in charge.
That's a fascinating model. You're basically hacking the brain's priority list. But let's pivot now. We've been talking about kids where the system is still under construction. Weismer spends the whole second half of the chapter on adults with neurological damage, strokes.
Right, and this is where the detective work gets even more complicated. Here we're dealing with a system that's been broken, not one that's being built. And for a long time, scientists thought they had the perfect diagnostic tool.
And this is VOT, voice onset time.
Yes, VOT.
It's a bit technical, so let's break it down. What is it measuring?
It's all about timing. To make a consonant like P or B, your lips pop open to release a burst of air. A moment later, your vocal cords start vibrating to make the vowel sound.
Okay, a pop, then a buzz.
VOT is just the time gap, the delay between the pop and the buzz. For a voiceless sound like P or T, there's a long delay. A puff of air escapes first. We call that a long lag.
And for a voiced sound like B or D?
The buzz starts almost instantly. A short lag.
So long gap means T, short gap means D. Simple.
In English, yes. And so researchers thought, this is it. We can map brain damage with this. They looked at the two main kinds of aphasia, Broca's and Wernicke's.
Let's do a quick refresher. Wernicke's is damage in the back of the brain. They can speak fluently, but it's often nonsense.
Correct. The old theory was that Wernicke's is a software problem. They're selecting the wrong sound file from their mental dictionary. So they mean to say time, but they pull the file for dime.
And if they select dime, they produce a perfect dime, a perfect short lag VOT.
Exactly. The machine works perfectly, it just got the wrong command.
Then you have Broca's aphasia, damage in the front of the brain. These are the patients who really struggle to get words out. It sounds like a physical effort.
Right. So the theory there was that this is a hardware problem. They have the right plan. They want to say time, but their motor system is glitchy and can't execute it properly.
So their VOT wouldn't be a clear T or a clear D. It would be somewhere in the middle. Messy.
A distortion, not a substitution. It was a beautiful, clean binary theory.
And whenever a theory is that clean,
It's almost always wrong.
Hewitt.
Later studies just show that the distinction completely falls apart. Broca's patients make what look like perfect substitutions, and Wernicke's patients sometimes have messy, distorted timing. It's all mixed up.
So you can't just listen to the sound and know what part of the brain failed.
No. And this is Weismer's central argument. He says we're falling into a major logic trap by looking at the acoustic result and assuming we know the physiological cause.
What's the trap? I mean, how can a correct plan result in the wrong sound?
Let's go back to that two sound. To make your vocal cords stop vibrating for that puff of air, your brain sends a command called the laryngeal devoicing gesture, or LDG.
LDG.
It's a ballistic gesture, like firing a cannon. Once the signal is sent, it happens. You can't really stop it halfway through.
So if the LDG cannon fires, that means the software worked. The brain's plan was, in fact, T.
Yes, but, and this is the whole mystery, the cannon has to fire at the exact right millisecond relative to your mouth opening.
Oh, I think I see where this is going. It's a timing issue.
It's all a timing issue. If the brain sends the open vocal cords command, but the mouth opens just a fraction of a second too late,
The puff of air gets lost.
the window of opportunity for that long lag is missed. So the plan was T. The physiology of the T happened, but the sound that comes out, the acoustic signal, has a short lag. It sounds like a D.
And I, as the researcher, look at my computer screen and say, aha, a phonemic error, a software bug.
But you'd be wrong. The software was fine. The hardware just had a timing slip.
Wow, that's a huge difference. Is there any way to catch that? To prove the cannon actually fired?
Sometimes. If you look incredibly closely at the recording, you can sometimes see a tiny little hiss of air leaking out just before the main sound. It's called pre-aspiration.
Like a little ghost of the intended sound.
Exactly. That little hiss is proof positive that the vocal cords were open. It proves the brain tried to make the T. It vindicates the software.
And the text drives this home by talking about dysarthria, right?
Right. That's the final nail in the coffin for that old binary theory. Dysarthria is a pure motor control problem. There are no software bugs. It's all muscle weakness or coordination.
Let me guess. Their VOTs look messy.
They produce the exact same phonemic-looking substitution errors that the aphasia patients do. So if the pure hardware patients look identical to the supposed software patients,
Then our whole way of classifying the errors is flawed.
it means we can't just trust a black box model. Just because a model can describe the output, oh, a key became a D, that doesn't mean for a second that it explains what happened inside the box.
It all comes back to the beginning. The kid saying fis or the stroke survivor saying dime. The mistake you hear on the surface is just a symptom. The real cause could be something completely different.
And Weismer ends with this really fascinating, provocative thought. Everything we've discussed today, all these timing rules for VOT, it's all based on English.
Right, that long lag for T is a very English thing.
But what about French or Thai? Their timing rules are completely different. In Thai, you have tones that depend on these fine-grained distinctions.
So if our entire model for diagnosing brain damage is built on the specific acoustic properties of English,
We might have a great theory of English aphasia, but not human aphasia.
Mm.
If VOT data can be this misleading in our own language, just imagine what we might be missing by not looking at these disorders in a wider cross-linguistic context.
You might find that the brain appears to break down in totally different ways, just depending on the language it was running.
It's very possible. The very structure of your native language might create the fault lines for where motor control is most likely to fail.
That's a heavy thought, that the software, the hardware, and the culture they operate in are all just completely inseparable.
It definitely keeps the field humble. There's a lot we still don't know.
Well, this has certainly made me hyper aware of the tiny ballistic miracle my mouth is performing right now.
It's amazing any of us can speak coherently at all, really.
A miracle of timing. Thank you so much for walking us through all this.
My pleasure.
And for everyone listening, next time you misspeak, just remember, it's probably not a software bug. Just a tiny timing glitch in your personal laryngeal devoicing system. We'll see you on the next deep dive.